Welcome to our Learning for Knowledge YouTube channel. This video is the second part of the antiscalants used in the water treatment or reverse osmosis systems. In this part 2, we will describe the operational performance and how can we evaluate the antiscalant performance when they are used for the scale inhibition in these processes. So we will move towards video. Processes. Now we will describe their operational performance and how can we evaluate which parameters affect their performance in this video. So antiscalant, which are also known as scale inhibitors or sequestering agents, nowadays are used to prevent these mineral scaling formation in desalination and heat exchanger processes. And these antiscalants retard the nucleation and growth of the mineral scale crystals or particles on the surfaces. So scale formation can be prevented by the addition of these antiscalant dispersants to the source water. So these antiscalant, as we already described in our first video, with the help of different mechanisms, they will prevent scale forming compound to settle on the surfaces. Now, after knowing different mechanisms, we will now focus on proper and accurate evaluation of inhibition performance can provide useful guidance regarding how can we select the best antiscalant and their approximate doses for the effective utilization of antiscalant. So that in short, we will perform some experiment for the selection of antiscalant and proper or exact dose which will be effective for the utilization of these antiscalants. So in general, there are two broad categories. One is static and second is dynamic. These different methodologies are used for the evaluation of the performance of the scale inhibitors. In static methods, there are different static methods like static jar test, bubble method, turbidity method, conductivity method, and constant composition precipitation method. These different methods, which are called static methods, are used for the evaluation or indication. Best word is indication, that how these antiscalant will perform when there are different type of scale forming species are present in a water or in a solution. One of the most common method is static jar test method. Basically, in this method, the apparent inhibition efficiency of the antiscalant is directly measured by using a solution, not flowing water, and the difference at the different solute, that is different scale forming species concentration. So we will put antiscalant, and we already have some known concentration of solute in the water, and we will check the effect of these antiscalant, how these interact with the impurities or the solute particle present in the water. So the effect of antiscalant on scale crystal morphology and the degrees of crystal distortion can be verified by using electron microscope and X-ray diffraction, because when we add the antiscalant in the solution which is present in the jar, it will react with those impurities, and whether it will settle or keep them in the suspended form in the water, these can be checked by the help of some other techniques like electron microscopy, etc. However, these static methods have limitations, and they are not fully applicable and inconsistent with practical conditions, because these are static and no simulated conditions can be applied in these methods. So considerable difference from practical conditions also exist in other static methods as well. Basically, these test methods are not of practical use, but they can be used as pre-evaluation approach, that if we have a different antiscalant and we have a different type of impurities, we will just use them for indication, and we can at the first stage evaluate these antiscalant effective against these sort of impurities and other sort of scale forming species. So this is basically pre-evaluation approach. Now in dynamic method, basically what we will do is we will use some practical simulation, and we have a prototype system in the laboratory which is used to check the performance of the antiscalant. So normally a laboratory scale RO unit is typically used to simulate an actual RO process. The scale inhibition performance can be determined by comparing the changes in permeate flux with and without antiscalant addition. How the addition of antiscalant affect the permeate quality, permeate quantity is determined by the addition or without addition on this prototype RO system, which is placed in the laboratory. So to evaluate scale surface coverage that can reflect the effectiveness of antiscalants can be monitored by using electron microscopy. That is, when we use the antiscalant, we will check the surface. When we will not use the antiscalant, we will check the surface with electron microscope and see how much scale is formed on the surface. So if we compare these two approaches, that is static and dynamic, then the operational conditions of RO simulation tests can be closer to those of actual RO system, and we can also adjust, because that is a prototype system, we can adjust the pressure, cross flow velocity, we can also adjust the feed spacer of the RO membrane and some other parameters like temperature, concentration, and so on. So these evaluation results, which are obtained from dynamic RO simulation, are definitely more helpful and more closer to the system and tell the actual performance of the RO antiscalant. Now we will discuss the influencing factors which can affect the properties. Basically, these factors affect the properties of feed water, antiscalant, scale formation behavior, and operation of reverse osmosis, and ultimately affect the final inhibition efficiency of the antiscalant. So these are some common factors, very famous, not unusual, like how much we will dose antiscalant in the system, what is the pH of the feed water, what are the operating temperature, and what are the impurities present, or you can say different coexisting substances in the water. So first of all, we will discuss the pH. pH is an important factor that affects inhibition performance, because pH can change the solubility of many types of minerals. That is, the solubility of many salts depend upon the pH of the water, and also charge properties of most ionic antiscalant in the water. So for example, the solubility of many of the carbonate minerals, they depend on pH. As pH decreases, that is, as we make the water more acidic, carbonates ions transform themselves into bicarbonate, and the solubility of bicarbonate mineral increases accordingly. As pH go down, so you can say the carbonates start dissolving and solubilizing in the water. Similarly, a low feed pH resulted in a low fouling tendency of RO membrane, which can be attributed to the scaling elimination of iron at low pH, because at low pH these metallic compounds start dissolving in the water, and if pH start increasing, they have a tendency to precipitate on the surface. By contrast, the solubility of amorphous silica SiO2 is relatively constant at near neutral or acidic pH, but its solubility increases above pH 8 to 9. So changes in pH can be effective for preventing scaling or certain scaling species, whose solubility and speciation are sensitive to pH, such as calcium carbonate and silica. So we have to be very careful that what type of scaling we are targeting. If we are targeting the carbonate scaling, we need to reduce the pH, we need to bring the pH down, but for solubility of silica we need to slightly increase the pH. So we have to make a decision what is the best pH to avoid the scaling. So anti-scaling with ionic functional groups can convert from protonation to deprotonation, that is, the proton which is attached on the antiscalant and now removed when pH gradually increase. Why? Because when we increase the pH, it means the hydrogen ion in the water are now becoming less. So the protons or the hydrogen ion are attached on the antiscalant. They are now start coming out from the antiscalant and now they try to live in the water to create an equilibrium. So the interactions between antiscalant and scale forming substances accordingly change, so influencing the inhibition performance. In short, the pH plays very important role not in the nature or in the pH will affect the dissolving capacity of the ions as well as it also affect the performance of antiscalant. Now the other important point is dosing point too close to acid addition, that is the dosing point of antiscalant is very close to acid addition point because we are adding the acid to control the pH and we are adding antiscalant to control the scaling. So pH is basically typically adjusted by the addition of sulfuric acid. If the sulfuric acid is not properly mixed, then it will affect the antiscalant. That is, the acid will temporarily form a separate phase due to its very high density relative to water. So if we dose or if we add the antiscalant very close to the acid, that is, then the acid can hydrolyze the antiscalant because it has a strong acid nature. So in short, if the antiscalant is dosed immediately after the acid dosing point, it can be hydrolyzed, that is, antiscalant can be hydrolyzed by the strong acid. And certain polymer based antiscalants are very susceptible to this degradation, that is, the polymer or main backbone of the antiscalant will be degraded. So we have to create both dosing points at a certain distance so there will be no effect, or you can say that before we add the antiscalant, the acid is completely dissolved and perform its function before it will come to the antiscalant. So there must be a reasonable distance in the addition of both of these things. And third is temperature. Temperature basically also affect for scale formation and affect the utilization of antiscalant because temperature affect the scale, crystal scale growth, mineral solubility, mass transfer in RO system, biofouling, and also plays role in the interaction between antiscalant and foulants. For example, the temperature effect should be considered in practical situation, like increasing temperature will increase the nucleation rate, that is, more crystal will be formed when the supersaturation ratio S is kept constant. However, solubility can also be influenced by the temperature change affecting the supersaturation ratio. Maybe in some cases temperature increase the solubility, and in few cases by increasing the temperature the solubility decreases, and this is an interesting phenomenon. Now calcium carbonate and calcium sulfate, in these cases the nucleation rate, that is the crystal formation started, is typically improved with increase in temperature, and water and solute permeability and mass transfer are usually enhanced as temperature increases. which can simultaneously reduce energy consumption and solute. In another video which we already discussed on the reverse osmosis system, we discussed the effect of temperature on the permeation or water quantity flow of the membrane, and we saw that by increasing temperature the permeate also increased, because now the molecule of the water can easily pass through the membrane. By increasing the temperature, more energy is available, and also it can help that more clean water is passed and less energy, less pressure is required for getting the product water in the RO, and this will help us in reduce energy consumption and solute rejection. More solute will be rejected because most of the salt will not pass through that. However, the above mentioned opposite effects of a high temperature operation leads high water recovery and low energy consumption, but this also leads higher scaling risk, because when more water is passed through that, more quantity of water basically enter in the RO membrane, and more quantity of water left or passed through the membrane, and it will left with a more quantity of the solutes, and which already contain some scaling compounds, and so scaling on the membrane surface increased. Another effect is coexisting substances, that is existence of other impurities. So there are a lot of impurities exist in water, and the scaling propensity of sparingly soluble salts, which have less soluble in the water, may influence by the existence of other pollutants like organic matter and inorganic ion, which further affect the utilization of antiscalants. Now, because there are different complicated physiochemical interactions exist between scale forming substances, antiscalants, membrane and impurities, and these complicated physiochemical interactions basically influence the scale formation by accelerating or inhibiting crystallization process. It depend, it can go on both sides, that these interactions may lead to the crystallization or maybe inhibiting the crystallization processes. So these interactions are strongly influenced by the environmental factors affecting the inhibition performance of antiscalant and scaling behavior in actual operation. That's why basically we perform some tests which cover under the heading of static or dynamic test, and we check the presence of many coexisting substances and check which antiscalant or which dose of the antiscalant will be more better or more convenient to control the scale. So the effect of existing multiple inorganic ions may influence scale formation or inhibition of the antiscalant. For example, gypsum crystal growth, gypsum which is present in the water in the presence of bicarbonate, and the formation of calcium carbonate scale in the gypsum dominant membrane system were retarded. This is that if we have more gypsum, then the crystallization or crystal formation of calcium carbonate is retarded. More, so less scaling will be formed due to calcium carbonate. Or in the presence of zinc ion, it can also influence scale precipitation, which can hinder calcium carbonate precipitation and change crystal morphology. So presence of zinc, there are some scale inhibitors by some companies that is based on zinc. They add zinc and it will retard the calcium carbonate scale formation by distorting or retarding the crystal morphology of calcium carbonate. So due to existence, these are the examples which shows that due to presence of some coexisting substances, the scale formation may increase or retard depending upon the existing impurities. Sometimes some companies intentionally use these type of compounds in their anti-scaling formulation, so it can stop or reduce the scale formation. Now, existing problems and perspectives. Now, antiscalants play a significant role in preventing scale formation, which we already know. However, there are certain practical problems and weaknesses exist with the addition of these antiscalants. Some of these are they can enhance bacterial growth on the surface of the membrane. Appropriate dosing control is very important issue, and then final concentrate disposal nowadays is also becoming an important issue. Antiscalant can effectively inhibit scale formation. However, antiscalants may alter the physical chemical surface properties of membrane via adsorption. So if they are overdosed, and by this phenomena, this will increase or enhance the biofouling of the membrane. So membrane surface charges, roughness and hydrophobicity are important factors that influence membrane organic fouling and biofilm formation. These properties of membrane surface can affect by the adsorption of antiscalant and promoting membrane organic fouling. And this is basically provide the feed for bacteria cells which can grow easily on the surface of the membrane. So common commercial phosphorus based antiscalants also a nutritional source of bacterial growth and enhanced not only by the phosphorus base but also synthetic polymer antiscalant. So this is one of the major drawback, and we have to focus on the dose control. If we will add more dosage occur of the antiscalant, definitely it will increase the biofouling. So dosing control is important, and performance of antiscalant depend on dose. An inappropriate dose will lead to increased membrane fouling, or if we dose less amount of antiscalant, then the efficiency of the inhibition will reduce. So antiscalant dose should be optimized in order to limit the not only chemical cost but also the proper performance. To avoid overdosing, so it is recommended that to apply minimum viable dose. So we have to start with very minimum dose. When we perform testing, then we should start from the lowest side, not on the other side. So maybe you can add 0.25 milligram per liter and then gradually increase until we reach at a point where the performance of antiscalant is optimized. And some companies basically recommend by using this software which in which we have to input some of the parameters, and then it will provide what type of dose is appropriate for this type of water. And acid dosing or softening can be easily monitored using pH or ion selective electrode. However, the monitoring of antiscalant are troublesome and require measurement using large scale instrument, which is sometimes difficult. So we have to rely on some of the dynamic testing or some of the hit and trial to check these effectiveness of this antiscalant. So effective antiscalant dosing and good pH control of the system can be operated significantly higher recoveries, that is more water product per unit of feed water. This is why nearly 6% of operating costs can be spent on the dosing of antiscalant chemical at the few ppm level. This is a generalized figure that in operating costs we can maximum 6% we can spend on the optimization of antiscalant chemicals. Now another important thing is if there is a high hardness present in the feed water, then there is a tendency of scale formation. Now higher negative charge, then antiscalant basically carries a higher negative charge than typically scale forming anions such as carbonate or phosphate which are present in the water. So they have a strong attraction to calcium and magnesium. During threshold inhibition, this attraction causes interference with the formation of a stable nucleus. However, when hardness are very high and antiscalant can form an insoluble calcium antiscalant salt. This causes another problem because once the active inhibitor precipitates, other scale will also precipitate. Because when inhibitor start precipitating, instead of capturing that ion and make them in the suspended in the water, if they precipitate, then other scale following scale will also precipitate, and hardness impacts all antiscalants regardless whether they are polymer or phosphonate base. And final important issue is the concentrate disposal, because the antiscalants which are used to inhibit the scale, they will go into the concentrate, and the concentration of antiscalant is higher in the concentrate, and the disposal of this concentrate become a problem due to environmental issues. So, due to anti-precipitation effect of antiscalant and appropriate concentrate pretreatment. So, there is an, because these are not easily precipitate and they have properties of anti-precipitation, so they are normally found in the water. So we required some other treatment, so we can remove by precipitation of with these antiscalants, and so the water which is disposed of must do not have these antiscalant present. So an appropriate concentrate pre-treatment can remove or degrade antiscalant is favorable for improving the performance of the succeeding concentrate treatment. So antiscalants, particularly biodegradable ones, can easily degrade under certain conditions, such as enzyme catalyst. So in summary, the effect of antiscalant on concentrate disposal and effective methods to mitigate their adverse effect are still there. These are consideration, and there is no specific solution now exists nowadays, but people are working on this to resolve these issues. So in short, antiscalant can be used with caution. Now in the presence of high level of iron, antiscalants made up of polyacrylic acid are susceptible. These are practical considerations to the formation of a foulant that settles on the membrane surface. This foulant will increase feed pressure requirement, can be cleaned using a low pH cleaning. So if we have a high iron and antiscalant is based on polyacrylic acid, then the foulant which is settled on the surface can be cleaned using low pH. So, and antiscalants are anionic in nature, that is polyacrylic acid. When a cation based coagulant or filtering aid is used in the pre-treatment, a very viscous sticky foulant can be produced that will increase feed pressure requirement, and it is very difficult to clean in off. So when we are using some coagulant or flocculation agent before the treatment, then due to presence of this coagulant, antiscalant will interact with this coagulant and they will form a sticky material which will stick on the membranes or surfaces, and it is difficult to remove those material. Now when you are going to buy some of the antiscalants then from the supplier, then there are some general questions which we must ask from the supplier. What are these questions? Is it compatible with the RO membrane type in question, that is the type of membrane which you are using, and these antiscalant which the supplier is supplying must be compatible. So is there a list of end user with successful operation that the company which is supplying you has other successful clients with them and they rely on their antiscalant? Or does it react adversely with any other constituent in the RO feed water? Example, iron, heavy metal, cationic, polyelectrolyte, etc., which I described on the previous page. What are the recommended dosing rates and maximum dosing rate? That is, what are the maximum dosing rate cutoff limit? Because more dosing, and if somebody is supplying you an antiscalant which you need to be dosed in a very high rate, then it will not be cost effective, and also you know that it will create biofouling as well. What are the projected limits of solubility for individual scaling and fouling components? Because antiscalant affect the solubility of these scaling compounds. So what are the limits they are providing, that this much amount of the scalant if present, then they can control these antiscalant. Are there any special discharge concern, that is whether they are environment friendly or they will not create any problem in the concentrate disposal? Does the supplier offer other RO chemical feeds like antiscalant, compatible, coagulant, biocide, etc.? Does the supplier offer off-site technical support services like membrane autopsies or cleaning of elements if we require that during the operation of our system? So these are the some important questions which one should ask from the supplier, generalize, and then after getting the answer, you can decide what type of antiscalant is suitable for you. But before asking these questions, you also have some water analysis and membrane material type in your hand, so you can